Starting with a constant function. In this graph, the output always stays the same no matter what x is. This is a horizontal line crossing the y-axis at b. The line never rises or falls, which means that the slope is always 0. And if there is no change as you go right or left, then the rate of change is 0 everywhere. And also, this is the visual representation of what the derivative of a constant looks like. Next, the linear function. This graph changes at a constant rate. The b is the starting height, the m is the slope, where if m is bigger than 0, then the line rises to the right, and if the slope is below 0, then the line falls to the right. But if the slope is 0, then the line reduces to the line of a constant. In here, the derivative is the same everywhere. Moving on to the power functions. We have x raised to the power of 2, meaning x squared, which is the classic parabola. This graph always opens upwards. It is a symbol for symmetry, and notice that both of the ends rise. In here, negative numbers become positive, and this is because when you square any number, whether positive or negative, you have to multiply it by itself, neutralizing those that are negative, which is why f of negative x equals f positive x, and this is called even symmetry. Moving on, we have x raised to the power of 3, meaning x cubed, or the S-shaped curve. This line grows from the bottom left to the top right, and it passes through the origin. In here, negative values remain negative, since multiplying a negative number by itself 3 times will keep the same sign. And that is why f of negative x equals negative f of x. This is called odd symmetry. Now x raised to the power of 4 is a similar graph to x squared since both are even. Some traits about this line is that near 0 it is flatter and it is steeper far away, and this is because the graph grows faster. In even-powered graphs, there is symmetry since the graph is equal left and right, creating a mirror symmetry across the y-axis. Even-powered graphs are always positive as well, and x raised to the power of 5 is the same as x cubed, but flatter near 0 and steeper far away. In here, negative remains negative and positive remains positive, so odd powers preserve direction and the graph rotates through the origin. Because if you rotate the bottom 180 degrees around the origin, it matches itself. Now let's talk about radical functions. First we have the square root, which is the same as to say x raised to the power of a half. The square root is the inverse relative of the power function. Power functions grow by multiplying numbers repeatedly. Root functions undo that growth. For example, 2 squared equals 4, while 4 raised to the power of a half is equal to 2. The square root reverses squaring, so x raised to the power of a half is the classic square root curve that starts at the origin and rises quickly, but slows down and flattens, and it only exists for real numbers, that is, x equal to or bigger than 0. And the square root of negative 1 is not real and therefore it has no line. Next, we have x raised to the power of 1/3. This is the cube root. This graph passes through the origin and exists for all real numbers, because negative numbers can stay negative with odd powers. As an example, negative 2 cubed equals negative 8, so the cube root of negative 8 is equal to negative 2, so odd roots preserve sign. Now x raised to the power of 1/4 is similar to the square root, defined for positive real numbers, starts at the origin and grows slowly. The bigger the x, the slower it grows. Now x raised to the power of 1/5 is similar to the cube root. It exists for negative and positive values, and it crosses through the origin and preserves whatever sign x has. So the graphs of roots grow very slowly compared to the graphs of powers because they compress large numbers. Moving on to rational functions. First, we have f of x equals 1 over x, which is the same to say x raised to the power of negative 1. This can be thought of as the inverse power function as well. These functions show what happens when growth turns into division instead of multiplication. Also, division by 0 is not possible, so all of these have a vertical asymptote at x equals 0. Note that there are 2 branches, one at quadrant 1 and another at quadrant 3, and as x goes to 0, the function explodes to positive and negative infinity, and as x goes to infinity, the function goes to 0. This is known as the hyperbola. Next, f of x equals 1 over x squared. In this graph, both sides are positive and it is symmetric about the y-axis, making it an even function. Now f of x equals 1 over x cubed. This graph is similar to the first odd rational function, but it is steeper near 0. And again, this graph preserves the negative sign, giving it odd symmetry. And we have branches at quadrants 1 and 3, with a more dramatic curve. And f of x equals 1 over x raised to the power of 4 is similar to the first even rational function, and this graph is always positive and has y-axis mirror symmetry. There is an even stronger blow-up near 0, so it rises very sharply near that area and flattens extremely fast as x grows. But when the denominator is big, the values shrink towards 0. Exponential functions. First, we have b raised to the power of x, where b is bigger than 1. This graph depicts continuous growth. It rises slowly and then fast. As x goes to infinity, the function goes to infinity as well. And as x goes to negative infinity, the function goes towards 0. So it has a horizontal asymptote at y equals 0. The graph for b smaller than 1 shows exponential decay. It is high on the left, drops quickly, and flattens near 0 on the right. As x goes to infinity, the function goes to 0. And as x goes to negative infinity, the function goes to positive infinity. There is also a horizontal asymptote at y equals 0. There is no even or odd symmetry here, and also note that every exponential graph passes through the point x equals 0 and y equals 1, because f of 0 equals 1 since b raised to the power of 0 is 1. Now let's move on to the log function, where f of x equals log b of x, where b is bigger than 0 and b is not equal to 1. Logarithms are the inverse of exponential functions. B raised to the power of x and log b of x undo each other. And here's an example. 2 cubed equals 8, so the log 2 of 8 equals 3. This graph rises quickly at first and then slows down more and more. It grows forever but slowly. There is a vertical asymptote at x equals 0 because the log b of 0 does not exist. And as x goes to 0 from the right, the function goes to negative infinity. Moving on to trigonometric functions, starting off with a sine function. Trig functions repeat in cycles. They model anything that is cyclical, like light, sound, seasons, and circular motion. This wave oscillates between -1 and 1 and repeats every 2 pi. This is an odd function since sine of negative x equals negative sine of x, and this also has rotational symmetry about the origin. Moving on to the cosine function, this one starts at 1 and oscillates between -1 and 1 as well. It also repeats every 2 pi and it is an even function. Cosine of negative x equals cosine of x, which mirrors across the y-axis. Both sine and cosine are essentially the same wave, just shifted in time. Lastly, the tangent function. This graph passes through the origin, rises steeply, and breaks apart. Because tan x equals sine x over cos x, then when cosine of x is equal to 0, you're dividing by 0, which creates those breaks on the graph. This graph repeats every pi and is odd since tan of negative x equals negative tan of x, and the tangent wave connects waves to rational function behavior.